Okay, good evening, everybody.
Good evening, Professor.
Welcome to another session of organic chemistry. In today's session, we are going to start our discussion on Chapter 10. Chapter 10 is concerned with the chemistry of organohalides. Okay, before we start, I have only one announcement to make. The homework assignment for this week is the Chapter 10 end of chapter questions in R, and the due date is Sunday, November 10 at 11 p.m. Okay, so that is Chapter 10 R, end of chapter questions. Due date is Sunday, November 10 at 11 p.m. Okay, so now in our discussion of organohalides chemistry, the good news is most of the topics that we are going to cover in this chapter, most of these we have actually covered in previous chapters. Okay. For example, when it comes to the nomenclature of organohalides, we've done that in previous chapters. The hydrohalogenation, when it comes to the synthesis of organohalides, we've done hydrohalogenation of alkenes and alkynes. We've also done the halogenation of alkenes and alkynes. Okay, so we do have very few topics to cover in this chapter. Hopefully, we should be able to finish this today, and then go and do some problems. And if we are able to finish Chapter 10 today and then do problems today, maybe we might be able to start Chapter 11. Right? You like that, right? Okay, anyway. So we are going to start Chapter 10 today. I think we should be able to finish Chapter 10 today. Of course, on this slide, you have a list of outcome objectives. These are the list of topics and concepts that you should master upon completion of this chapter. So I will advise you to use this list of outcome objectives as a study guide for studying the content of this chapter. Because the next question is, what are organohalides? As you can see, organohalides are those organic compounds that contain one or more halogens. And when we say halogens, we mean the fluorine, chlorine, bromine, iodine. Okay, so that basically those are the halogens that we refer to, we will be treating with regard to organohalide chemistry. And as you can see here, for the nomenclature of these compounds, the halogens are treated as substituents. Here, when you consider the halogens as substituents, then the fluorine becomes fluoro, chlorine becomes chloro, bromine bromo, and iodine iodo. Okay, all of this we've done before, so we don't really need to spend any time on this. For example, you have this molecule here, iodomethane. That would be the IUPAC name. Of course, the common name for this is also we call methyl iodide. That would be the common name, in which all you do is simply just give the name of the alkyl group and then also the name of the halogen. Here, the common name for this molecule here would be cyclohexyl bromide. However, for our purpose in this chapter, I will encourage you to use the IUPAC name. Okay? Okay, so what I want to do now, since we have already treated most of the nomenclature of these compounds, what I want to do is to go straight to the synthesis of the organohalides. Okay. Synthesis of organohalides. Okay, what I want to do first, I am going to list all of the various synthetic methods and then subsequently go in details with each one of them. So one, you have the free radical substitution of hydrogen attached to sp3 carbon. That is very important. Free radical substitution of hydrogens attached to sp3 carbon using bromine and chlorine in the presence of light or heat. Light or heat. Okay, so that is one method. We are going to go into details with that subsequently. Method number 2. Free radical substitution of hydrogen attached to allylic sp3 carbon using N-bromosuccinimide. N-bromosuccinimide. N-bromosuccinimide we abbreviate as NBS. Okay, method number 3. Substitution of OH group attached to sp3 carbon using, okay, let me, before I write using, let me put parentheses here. Should be alcohol. That would be alcohol. Okay, OH group attached to sp3 carbon, that would be an alcohol. Okay, using HCl gas, HBr gas, hydrogen iodide gas, thionyl chloride, this molecule here, and phosphorus tribromide. No, I will write the name later. SOCl2, we call thionyl chloride. Well, let me go ahead and do that now. Thionyl chloride and phosphorus tribromide, PBr3, phosphorus. Yeah. Of course, the other two methods that I told you that we've used before, let me go ahead and list those also. For hydrohalogenation of alkenes and alkynes that we've done before. Of alkenes and alkynes. And what that is essentially just adding hydrogen and halogen across the carbon-carbon double bond or across the carbon-carbon triple bond. Okay. Number 5, halogenation of alkenes and alkynes. Okay. Methods number 1, 2, and 3, those are the methods we are going to discuss now. So 4 and 5 we've already done in earlier chapters. Okay, so let us start with 1. Free radical halogenation. If, for example, we take this, I think we've done this also before, but this time I do want to give you the mechanism. If, for example, we take this, we take methane, and we take chlorine, take this out. We take chlorine or bromine in the presence of light or heat. Forget this. So here, what we have done here, we have replaced one of these hydrogen here that is attached to an sp3 carbon. We have replaced that hydrogen with chlorine. Okay, so let us give you the mechanism for this reaction. Of course, it doesn't have to be methane that we are using. We could also use, for example, We could use cyclohexane. Of course, you get this. As long as you have an hydrogen as attached to an sp3 carbon. We could have this. Oh, yes, thank you. We could have this. Okay, this hydrogen here will be the reactive hydrogen because these are attached to this sp3 carbon. Okay, this symbol here, that's the symbol for heat. Okay? So you get the idea. In other words, any hydrogen that is attached to an sp3 carbon, you react with, you could replace with chlorine or bromine in the presence of light or heat. Okay, so now let us now give you the mechanism for this reaction. Okay, to give you that mechanism, let me use this reaction here. Let us use this reaction here to demonstrate the mechanism of this reaction. Keep in mind, this is a general mechanism that applies to any of these type of reactions in which you are replacing an hydrogen attached to an sp3 carbon under free radical condition. Okay? Okay, keep in mind we want to use this molecule, this reaction here. Cyclohexane. I show this hydrogen just to give you to demonstrate the fact that we are going to be replacing this hydrogen. Okay. For the reaction mechanism, there are 3 steps. Recall when we discussed the synthesis of polymer plastic, I gave you also a free radical type reaction. The same set of reaction that we are also going to be discussing now. In other words, for this reaction here, you have 3 steps. You have what we call the initiation step. Then you have the propagation step. Then finally you have the termination step. Okay, so let us look at the initiation step. For the initiation step, the first thing that happens, here the chlorine molecule will undergo what we call an homolytic cleavage. In which this bonding electron here, the 2 bonding electrons, one will go to this chlorine here, and you notice how we use the fish hook arrow to show the movement of one electron, and then the other electron will go here. Okay, so now you have free radical. Now you have chlorine free radical. Okay. That is your initiation step. Now you come to the propagation step. The chlorine free radical that you form now will now react with the starting material. In this case, is cyclohexane, or it could be methane, or any molecule that contains hydrogen attached to an sp3 carbon atom. So you have this. This free radical here will now abstract or pull away this hydrogen here. In the process, this carbon-hydrogen bond will also cleave homolytically. Okay? In other words, one electron goes to here to form the new bond, and the other electron stays with this carbon here. So now we have this. Okay? Now this is the step of the reaction mechanism during which we are making or forming the, in this case, hydrogen chloride. Okay? That is the step of the reaction mechanism in which we are forming the hydrogen chloride. So now we've now also formed the organic free radical. I'll call this organic free radical. Okay? So that is the first step of the propagation step. So I'm going to designate this as 2A. In other words, propagation step has more than one step. Okay, 2A. And then the second part of the propagation step, I'll call it B. What happens now? The organic free radical comes back. And now react with another molecule of chlorine. Now, if you are using bromine, it will be the same reaction mechanism. Okay, so keep that in mind. Okay, so the chlorine bond will also cleave homolytically, in which this will now come in, attach itself to this carbon here. Of course, that electron also is now used to form a new carbon-chlorine bond.
But why do you have two chlorines there if they already cleaved in the first step?
Which one?
Why do you have two chlorines there if they already cleaved in the first step?
No, that is just the initiation step. Because that this chlorine, this radical here, what it does is to come here to do this, react with this alkane. Okay?
So what happens to the other free radicals?
Oh, it's just floating, it's still there. It's just floating around, yeah. Mm. Okay.
So two chlorines are still floating around even though one of them formed hydrochloride?
Yes, yes. Because do not forget, this is the product we have to form.
Okay.
We have to form this product. Okay, there is a lot of chlorine around. Okay, when you start, The initiation step, you only use very small amount of chlorine. So you do not use a lot of chlorine. So that is why you call it initiation step. Okay, now just wait. Now, at this point, you now have this. The second propagation step, what are you now doing? You now form your desired product. That is when you form that. And now you now regenerate another chlorine radical, free radical. Okay? So this is the point at which we form the product, which is this product here. The second step of the propagation step, that is when you form the product. Now, this free radical that is now formed, now goes back. Now you have now formed a loop. Now goes back to start the propagation step all over again. Okay? Keep in mind the initiation step, you start with a very small amount of free radical. Just a very small amount of free radical. Because once the propagation starts, it generates the free radical by itself. So it's almost like you now have a loop, keep going until all the chlorine is gone. Okay? So now, the final step is what we call the termination step, which is this here. The termination step, okay, you set up the conditions such that most of the reactants have gone, most of the organic reactants have gone, most of the chlorine has gone, and then you have a lot of free radical around. Okay, that is when free radicals will now be joining together, and that terminates the process. Okay, so any two free radicals joining together, that would be a termination step. For example, you could have chlorine, another chlorine, to form chlorine. Okay, or you could have this organic free radical here. This organic free radical here. Okay, two organic free radicals coming together. Okay, so this would be an organic byproduct. This would be an organic byproduct. That would be an organic byproduct, yes.
So when does B and A combine to make the product?
With D and A.
Like the structure in B, that you circle green, and then in A, when you circle purple, like what do you...
This here?
So we don't have to show that they're together?
With two together.
A and B.
With A and B.
Two A and B.
No, this is, no, you get A start, you start with A first, okay? From A, then you generate the, this here, you go to B.
But I'm saying, you know how any other mechanism would do?
Mm.
We start with the product. We start with the reaction and end when you show the product.
Mm-hmm.
In this mechanism, like nowhere in the mechanism does it show the product at the top. You don't have to show that?
The product, this is the product.
But just go ahead, go ahead.
This is where we found the product.
At the very top, like you have the green and like the purple strip at where you're pointing, and then at a 2, then when you go down to 2A and 2B, you have to separate. Right. So like you have to, how do you
Okay, I see.
to show that?
Okay. This here, you know that this is a product, right? This is a product, okay? What we are showing you here, those two products are formed at different different times during in the course of the reaction mechanism. This here is formed at this step A of the propagation. This here, that is when it is formed, and this here the organic product that we really want is formed at the step B of the propagation step. Okay? Both of them are not formed at the same time. Huh? What are you getting? Okay. See? So remember, I used to tell you guys, do not worry about reaction mechanism. Now I give you mechanism. Okay, this is what you are going to get. Okay, I give you this. If I give you this, right? I say, give me the product. What would be the product? Exactly. That's the product. In other words, all this reagent is doing is going to replace an hydrogen attached to an sp3 carbon. Okay, so therefore it will be this here. But if I ask you to give the mechanism, then you have to go through this. Okay? Okay, so this is the product.
So, question, is the third step, is that the proper step corresponding to this reaction?
Yes.
Okay.
You see, what I've given you here, this is the reaction mechanism for this here. This is the mechanism for this reaction here. That is the mechanism for this reaction. Okay? Yes. What is byproduct? Oh, this organic byproduct. Okay, very good, very good. Supposing I say, very good. Supposing I do this. Right? Huh? She said this byproduct here. Okay? You say, where does this come in? Okay? Okay? That's the question she's asking. If I ask you to give me the mechanism for the formation of the organic byproduct, what that means, you have to go all the way to here. Okay? Yes, if I don't ask that, I say give me the mechanism for this reaction, for how we go from here to here. Okay, then you have to give me this mechanism, and at that point you could use any free radical to terminate the process. Okay. Mm-hmm. Yeah, if I just ask you, if I give you this reaction here, right, and I say give me the mechanism for this reaction. In other words, I am asking you, show me how this product is formed, how this is formed. Okay, in that case, you have to give me the complete mechanism that you have here, including the termination step, but you could use any termination step that you want, any of the free radicals to terminate the process. No, unless I ask you to give me the mechanism for the formation of the organic byproduct. Okay? Now, say that again. Exactly. Exactly. If I say, give me the mechanism that also gives the organic byproduct, at that point you have to give me a mechanism that includes the termination step in which you use the organic free radical to terminate the process. Okay, for example, supposing I add this. Supposing I give you this. Okay? Supposing I give you that. Bromine. Light. Okay? And I say, for this reaction here, give me the product of this reaction, and also give me the mechanism that also gives you an organic byproduct. Okay? I say, give me the reaction mechanism. Okay, two questions here. Give me the product. Okay? Give me all of the organic products. Give the organic products, okay? And give a mechanism that includes the formation of organic byproducts. Formation of organic byproduct. Okay? Okay. The first thing is, okay, let me label this. Let me number this. It's carbon 1, 2, 3, 4, 5, 6, no, yes, 7. Okay? What will be the product? Which carbon are we going to be joining together? What will be the products? All of the organic products, yes.
Some organic product is going to be a methyl bromocyclohexane. You know what I'm trying to say, right?
What is going to happen here? Which hydrogen are we replacing?
On the methyl.
No, what does this reagent do? What does this reagent do?
It breaks it and turns into radical.
What does it do? It replaces the, exactly, very good, thank you. It replaces the hydrogen attached to an sp3 carbon. In other words, one of these hydrogen will be replaced. Okay, you need to know, give this specific definition, because if you don't, you will be missing the point. Okay? So therefore, this reagent, what it does is to replace an hydrogen that is attached to an sp3 carbon. Very good. If you say that is what it gives you, therefore I expect you to give me this product. That will be an organic product. Okay? Yes. Huh? Oh, I think. So that will be the organic product. Now, what will be the organic byproduct?
Oh, that would be, you just take out the BR and form a bond with another.
Exactly. So the organic byproduct will be this here. Okay? And that will be the organic byproduct. Now, supposing that I tell you to give me the mechanism, I tell you to give me the mechanism of this reaction. Okay, I'm going to leave that to you guys. Okay? No, I'm not going to go through that. You should be able to do that, following what I just did. Okay, so when you go home, write the mechanism for this reaction right here. Okay? Okay, let us go to the next one. Okay, so now we have dealt with the free radical substitution of hydrogen attached to an sp3 carbon using bromine or chlorine in the presence of light. Now the second reaction, free radical substitution of allylic sp3 carbon using what we call MBS. Now, if you take this molecule here, If you take this molecule here, an allylic carbon is that carbon that is attached to a carbon-carbon double bond. So therefore, this carbon here, is what we call allylic carbons. Allylic carbon is that carbon that is attached to a carbon-carbon double bond. Okay, this is also an allylic carbon. And therefore, the hydrogen attached to an allylic carbon is called an allylic hydrogen. So these are allylic hydrogens.
Yeah.
The same thing here.
Why are those allylic?
Okay. Now, if I have this,
You got a double one.
huh?
You got a double one.
If I have this, okay, and you have this compound here, we call this N-bromosuccinimide. We abbreviate as MBS, so subsequently you guys could simply just write MBS. What this reagent does, of course, this reaction takes place in the presence of heat or light. What this reagent does is to only replace the hydrogen attached to an allylic carbon. So you will get this product here. That is what you are going to get. That's the product you are going to get. So if you only replace the hydrogen attached to which one? Yes, that is all it does. Okay. Laws to form this. Okay, this succinimide, this is succinimide. This is not of interest to you, but all you want is just this organohalide. If I ask you what is the product of this reaction, all you simply have to do is give me the organohalide product. Okay?
It doesn't do it on both ends.
Which one?
It doesn't, bromine doesn't test to the bottom.
No, just one end. Unless most of these reactions you could control them, unless you want to do multiple bromination, you could get multiple bromination. But if you simply want mono substitution, yes, you could control so that you get only the mono bromo product. Okay. Anyway, so that is what this reagent will do. So therefore, you could have this. Supposing we have this. NBS. Okay. What will be the product? What will be the product? Let's number this here. 1, 2, 3, and 4. What will be the product?
How do we know we're starting with
Huh? What is going to happen here? What does this NBS do? I want you to describe for me in your own words. Replaces that is attached to, okay, exactly. Okay, replaces an allylic hydrogen with bromine. That's what you guys have to be able to say this. If you don't say that, you will find that you will not be able to understand what is going on. When you say it, then you know what is happening. Okay? You need to say it in your own words. Okay? So this reagent here, what it does is to replace an allylic hydrogen with bromine. That's what it does. You have to be able to say that. Okay, and if you look at this molecule here, where are the allylic hydrogens? On carbon 1 and carbon 4. Okay, therefore, I will expect this product here now, what the NBS does, you have to think of NBS as a source of bromine and bromine radical. Think of NBS as a source of bromine and bromine radical. Okay? That is the way you look at it. Therefore, supposing I give you this reaction here, NBS reacting with this molecule to give this. And I say, give me the reaction mechanism. Then you have to give me the same mechanism that I gave you earlier, in which you already have the initiation step, this here, okay, this already here, and then bromine is here. Okay, so what NBS does is a source of bromine and bromine radical. So basically the mechanism for this reaction is the same reaction mechanism that I gave you earlier, which is this one here, as you see here. Which is this here. It's just that the starting material is different. Okay? So you could substitute this. Once you already have bromine radical here, bromine radical simply comes here. We now abstract the allylic hydrogen, and then the process will continue. Okay? Now, the problem with free radicals is this. Free radicals are very, very reactive. Okay? Okay, so let us see here. Free radical and resonance. Okay, if you have this, supposing I have this here, okay, supposing I have that, and I say that we have this NBS supposing, let us number this 1, 2, 3, 4, 5, and 6. What will be the product of this reaction? What will be the product of this reaction? Just tell me where. Okay, what does the MBS do?
Replaces an allylic hydrogen.
Okay, which allylic hydrogen is it going to replace? Give me the number of the carbon.
5 or 6.
Okay, carbon 5 and 6, the hydrogens on those carbon, right? Okay, very good. So we get this. Okay, we get that. That is fine. That is an allylic. We have replaced an allylic hydrogen. Okay. Yes. Which one? Yeah, they will be equivalent at this point. Yeah, they will be equivalent. Okay. Now, so this is, if you get this product here, what you are assuming here, knowing the reaction mechanism, okay, during the reaction mechanism, since we are forming this bromide here, this bromine is coming here, what does that tell us about the reaction mechanism? Where would be the free radical? Where would the free radical be?
It would be
Where?
when the bromine is
On carbon? Exactly. That means, that means, huh? Okay, knowing the reaction mechanism, okay, where will the free radical be during the reaction mechanism of this reaction? Where will it be? On what carbon? Carbon 6.
Yes.
Okay. Okay, so we say we have free radical here. We all agree to that. Okay, there's free radical here. Now this free radical here, of course this carbon here, of course this carbon also has hydrogen here already. This carbon here, at this point, is an sp2 carbon, right here, on this free radical. And then you have this carbon here, is also an sp2 carbon. This carbon here is also an sp2 carbon. So now you could think of the possibility of resonance here. Okay. So now what do we get? We now get a resonance structure in which we could have this. Double bond is now here. This double bond is here. Now the free radical is now here. Guess what? This free radical could react with what to form the product.
Oh, I see.
Can you like draw a bigger?
Draw what?
The arrows, like I really don't know where they are.
Oh, okay. Let me make it bigger. Okay, we start with this, and then we say the free radical is right here, okay, on that carbon. So what we're saying now, we could have this one electron moving here. Notice we're only moving one electron. This electron also moving here to now form a pi bond. And the other electron comes to this carbon here. Okay? So now we form this here. Okay? These two here, A and B, are resonance structures. Okay? These are two resonance structures. So now what you now have here, this could now react with your bromine. to form the product.
Yes, doesn't react with that either.
Huh? What?
Never mind. Okay.
So that last element was the right, is that a spaceship jump or that?
Oh, it's fish hook. Yeah, I'm sorry. That's a fish hook arrow. Thank you. Okay. Okay, so now we form this product. See what we've done now. See what have we done now. So this reaction here with MBS, this reactant here with MBS, in addition to forming this product here, it could also form this product. So I could ask you, I could simply give, instead of giving this here as the product, I could do this. Give a mechanism for that reaction. Okay? So what that is asking you to do, when you have to also give a mechanism in which you have to show resonance. Because that is the only way the free radical will be on this carbon. Okay? Now, what that's also going to show you is that whenever you have a free radical, if it is possible for the free radical to undergo resonance to form a more stable free radical, that will also always happen. Or at any given time, if you have the chance of forming the choices of free radical, for example, supposing we have this. Supposing we have this. Okay? If we have this, and I ask you, you may not be able to answer this question yet. I ask you, MBS is reacting with this here. Okay? MBS is reacting with this molecule here. And I say, give me the major product for this reaction. In order for you to do that, you need to know the order of stability of free radicals. So let us give that to you. Order of stability of free radicals. Okay? The most stable tertiary, or actually, let me start with allelic. Allelic, okay? More stable than tertiary, more stable than secondary, more stable than primary, and more stable than methyl. Okay, let's give an example of that. For example, we say this here. Okay, that would be allylic right here. Okay, and here, this is allylic on this carbon right here, and here this will be tertiary for this here, because here this here, this will be secondary, right? And here, so if I have one here, if I have tertiary here, and if I have one here, okay, here will be this will be primary, and of course, finally, we have the methyl. And this will be methyl. So that is the order of stability of free radicals. So whenever a reaction is going to take place, the major product will come from the more stable or the most stable free radical. So therefore, if I ask you, if I give you this here, let me go ahead and number this. Let's say position 1, 2, 3, 4, 5, 6. This just for the purpose of this discussion. 7. Okay? What will be the major product of this reaction? What will be the major product of this reaction? What does MBS do?
Yes, or replace allylic.
Okay, replace hydrogen attached to allylic carbon, right? How many allylic hydrogen? How many allylic carbon do you have here? We have 2 and 5. Okay. So where would be what would be the major product? Where would the major product be? On 2, because that is the allylic hydrogen that will give rise to the more stable free radical. Okay, so therefore, so that would be your major product. If I ask you what is the major product, that would be the major product. Okay, so there are many ways I will ask you this. Either I give the major product, or I could simply say give me the product, or sometimes give the reaction mechanism. Now, supposing we do the same thing with this. Bromine in the presence of light. What will be the major product? What will be the major product? Let me number this. 1, 2, and 3. What will be the major product?
Isn't this going back to the first reaction?
Huh?
Isn't this the first reaction that we did? Not
What is it?
You replace
Huh?
the hydrogen with the bromine.
Okay, yeah, it will replace the hydrogen with bromine. Which hydrogen will it replace?
One on the bottom.
One attached to carbon number 2, exactly. Very good. So therefore, this will be the major product.
Why didn't you put MBS? Why you put MBS?
Okay? Okay, so now we have given you the free radical, 2 sets of free radical reactions with halogenation and then with MBS. Now let us give you the third synthetic method for organohalides. I believe this is number 3. Okay, substitution of OH group attached to sp3 carbon. Okay. Okay. If we have this, okay, this is a tertiary alcohol. If you have a tertiary alcohol and you use HCl gas, okay, you will replace the hydroxy group with chlorine. That is what this reagent will do with a tertiary alcohol. Now, if you use the same thing will happen with HBr gas. Okay, what does it do? Replace the OH with bromine. This reaction is best with tertiary alcohol. Okay, with tertiary alcohol. Supposing you have a primary or secondary alcohol and you want to replace the OH group. In that case, supposing we have this. Okay, let me do this here. Supposing we have this. If you have that molecule here, you notice I am showing stereochemistry here because this reaction has stereochemical implication. Okay, actually. Okay. Let us say here. Oh, that's fine. We have this here, called this thionyl chloride. Okay, you get this product here. Okay, you get that product. So what does this reagent do? This reagent will replace an OH group with a chlorine atom. Okay. Of course, somewhere here you also form sulfur dioxide and HCl. When we go through the reaction mechanism, you see how that is formed. Those are formed. So what this reagent will do is to replace an OH group with a chlorine atom. But it does it in a way as to what we call invert, with inversion of configuration. You don't see with inversion of configuration. Okay. Supposing we started with a molecule that has a chirality center. Supposing we start with a molecule that has a chirality center. Let us say we start with this molecule here. And you use thionyl chloride. Use thionyl chloride. Whatever the absolute configuration of this carbon is, in the product it will be the opposite. So therefore, because this chlorine will come from the back, okay, so therefore you are going to get this product here. Chlorine will now be here. Okay, when you get home, figure out what the absolute configuration of this carbon is. Whatever it is, if this was R, you find out this would be S. If this was S, you find out this would be R. So this reaction here, even though it replaces the OH group with chlorine atom, it does have stereochemical implication. In other words, if you have a chirality carbon, whatever the absolute configuration of that carbon is, if you replace the OH group attached to that carbon using thionyl chloride, you are going to invert the configuration. And that is what we mean by inversion of configuration. Okay? Yes?
I was going to say, like, for example, if it was H, for the first example, there's no specific...
Well, there is no, that's why I use another... You know, in this case, you don't have to worry about it, because there is no stereochemistry really involved here. Okay? But whenever you have stereochemical chirality carbon here, then you actually do see the inversion of configuration.
Yeah, I was going to say for the first one, it has no tendency to go to the pro-R, pro-S carbon.
No, that's not what we are not replacing the hydrogen here. Okay, we are just replacing the OH. Okay. So anyway, so what does thionyl chloride do? Without worrying about the stereochemistry, if I simply just do this, and I do this, what do you get? You just replace the chlorine with the OH with chlorine. If I don't show you stereochemistry, just a simple case of replacement of OH with chlorine. Okay? Now another reagent that we could also use to form organohalo compounds is what we call phosphorus tribromide. What that does is also replace the OH with bromine. Now, both of these reagents here, thionyl chloride and phosphorus tribromide, the OH group must be attached to a primary or secondary carbon. Okay, let me write it down. OH group must be attached to primary or secondary carbon. Okay? Also, as in the case of the thionyl chloride, the reaction with phosphorus tribromide also proceed with inversion of configuration. Let me give you an example. Are you writing this? You got it? Okay. I do want to do a two problem. Okay. This here I will give you. Okay. And the phosphorus tribromide also proceed with inversion of configuration. For example, if we started with this, okay, and you react with phosphorus tribromide, okay, the product that we expect to get will be the one with inverted configuration. That would be the product I expect to get, because this reagent also will proceed with inversion of configuration. Okay, so at this point we have finished chapter 10. Do you want to do a couple of problems? Okay.
Yes, we do.
Let us see. Very simple one, very simple one. Okay, very simple one. Okay, Kiara, can you read this for us? Okay, what is the major organic product of this year? Only mono substituted product. Okay, let me number this to help you out. 1, 2, 3, 4, 5. Okay, where do you expect the bromine to go?
3.
3, very good. Okay. Okay, good.
Nice.
Oh. Yes. Huh?
No.
Carbon.
No. No.
You need to know, what does this reagent do? What does this reagent do? Exactly. Okay, thank you. I really can't see. Okay. As long as you know what it does, you will not be wrong. Okay, you need to say it out in your own words. Okay, everybody's next one here. Okay. Emeka, can you read this for us?
Draw the major organic products of the following reaction.
It should be fairly simple, right?
Yes.
What is it? Just replace. Is it how easy it is? Okay. Huh? Well, these are you like these kind of questions, right?
Do a resonance one. Do a resonance.
Okay, so this will be this here. Okay. Now. Okay. Okay. When you go home, work on this one before you come back. You go back.
No.
By the way, there will be a 10-minute quiz on Thursday on today's material. Okay. You want me to go to that other one? So anyway, I'm going to leave this to you for you to think about. Oh no, not that one. Think about this one here before you come back on Thursday. Provide a synthetic scheme for the following transformation. Okay? Think about that. Okay, and then there will be a short 10-minute quiz on Thursday, yes. That is why I post. Let me stop this here. Okay, folks, I will see you on Thursday.
We're having a quiz on these notes, right?
Yes, yes.